When we're talking about differentiability, what we're talking about is the ability for a function to be differentiated. Can we find the derivative of a function at a point? So when we're trying to find that derivative of a function at a specific point, what we come up with is the numerical derivative. And we know a couple things about it. First thing that we know is that it's the slope of the tangent line at that point. The other thing we know is that limit definition, so that if we wanted to find the derivative at some specific point A, we take the limit as x approaches A of f of x minus f of A over x minus A. So given those two small just pieces of information that we know about the numerical derivative, why is it that I can't find the derivative of the function at c? Right? So if this is our f of x, right, and I'm trying to find the derivative at c, well, c doesn't even exist. There is no point c, so we don't know where the derivative could be. So why this is not differentiable is because the function does not exist, not at f of x, but at f of c. Right? The function doesn't exist at c. But now I've got same function, f of x, but this time it is defined at c. C is this point set aside from the rest of the function. And why this one would not be differentiable is because, I mean, think about that tangent line definition. What does a tangent line look like at C? Does it look like this? Is it positive? Is it negative? I mean, all these tangent lines are kind of just teetering on that point C because C is not locked down into this function here. So why is it not differentiable at x equals C? Because f is not continuous at C. All right, well, this one's got to work, right? Because we have a function that is defined at C, and the function is continuous at C. That where C is exactly where we would expect it to be. But when it comes to our function, f of x, and we're trying to look at its derivative, we want to find that limit as x approaches C of the f of x minus f of c. And the thing about the limit is, in order for the limit to exist, that the left-hand limit and the right-hand limit have to be the same. We have to get the same value whether we're on the left side of C or the right side of C. And the thing about this limit is that this limit does not exist. Because if I was on the left side of C over here, I would expect my tangent lines to all be negative, right? Because the tangent lines are going down. As soon as we get to the right side of C, now all my tangent lines are going to be positive. All right, so from the left, we expect the negative number. From the right, we expect the positive number. Because they're not the same, that limit doesn't exist. And then obviously one more, where we have a vertical asymptote, there f of c doesn't exist here either. That you might think that whether we're coming at it from the left or from the right, we're expecting the slopes of that tangent line to be vertical, right? And well, a vertical slope has 0 in the denominator. It doesn't exist. An undefined slope doesn't exist. So really the long and the short of it is, when is a function differentiable at a point? As long as it satisfies two conditions. As long as it's continuous at that point, and as long as it's what we call smooth. right? There's no sharp turns, there's no cusps. That's when we're talking about like that absolute value function, or maybe a cusp looking like this. If it comes together at a point and it's not smooth, we don't know if our tangent line is going to be, positive, or if it's going to be negative, or if it's just kind of teetering on that peak. As soon as we get a function that is smooth, meaning that it's rounded at that top, then we are able to tell, what the derivative is there.